Hi, my name is Mira. Within the next few minutes, I'll give you some insights about how AVL FIRE M can help you developing batteries. FIRE M is a 3D CFD simulation software developed by AVL. Our battery solution focuses on active and passive safety aspects, helping to develop cells, modules, and packs that can be safely operated under all relevant charging and discharging conditions in the targeted environments. An important aspect in this regard is the thermal layout of a battery module or pack. Therefore, the cornerstone for each simulation model is the description of the heat source from the battery cells. The more accurate the description or model behind it, the better the battery can be optimized. FIRE M features multiple approaches, ranging from very simple models that just consider the heat release up to very detailed models that describe the full electrochemical state. The simplest model provides a constant heat output from the battery cell. This is a fast and reliable way for initial simulations in an early development stage, when not much of the layout is fixed yet. If the heat dissipation depends on the internal resistance of the battery and the electric current, the model is still of low complexity, but it allows the investigation of simple load case scenarios. Equivalent circuit models are available to model the transient behavior of the battery cell. These models are often used in other software applications, like the battery management system. The most in-depth approach offers to fully model the electrochemical processes in the battery. With this, also degradation and aging can be investigated. FIRE M is applicable on cell, module, and pack level. Also, simulating power electronics is within its focus. On cell level, electrochemical, or detailed spatial temperature resolution is most often in the foreground of the investigations. For battery modules and packs, the focus is more on their arrangement and thermal optimization for transient battery operation, as well as on avoiding hazards such as thermal runaway. Power electronics is closely linked to electrification. There is a great need for optimization, particularly for relays, switches, and inverters. Simulation is essential for solving related challenges. As you can see, FIRE M offers a comprehensive range of options to support battery development. And we offer even more. What you can simulate in FIRE M, you can also simulate in our multi-physics system simulation software, AVL, Cruise M. The aforementioned models and solutions are identically available in both FIRE M and Cruise M. This allows our clients to perform consistent simulations from single-cell layout to full-pack detailed design, while always being able to balance simulation performance and degree of modeling depth. The battery cooling layout does not only serve the purpose of battery performance optimization, it also contributes to active battery safety. In combination with the battery management system, overheating and/or overcharging of battery cells shall be prevented. But in case things go wrong and a battery cell goes into thermal runaway, it must be ensured that the thermal runaway does not propagate through the whole battery module or pack. That's why regulations demand a so-called no propagation design of battery packs. It is what is also called passive battery safety. This is needed as otherwise the entire battery module or pack could be destroyed, and more importantly, the vehicle occupants will be exposed to extreme danger. But can a simulation really help with understanding thermal runaway? Even physical tests are hardly able to reproduce the behavior. The answer is yes. And I'll let you know why. Thermal runaway is a critical challenge in battery development. Testing often delivers inconsistent results because there are so many physical effects that interact at once. These include, for example, rapid heat buildup from internal chemical reactions, electrolyte evaporation and venting of flammable gases, arcing, which can ignite the venting gas, and extreme thermal load, resulting in melting structures and deformation of cells. But using FIRE M, engineers can do: first, better understand the chain of events inside a cell. Second, explore scenarios that are dangerous or hardly reproducible in tests. And third, design safer and more robust battery systems. One more statement at this point. Our simulation solution is extremely powerful. Still, we do not claim to replace testing. We complement it in the best possible way. What does no propagation design mean? No propagation design starts at cell level, where cell tests give us the input data that are needed for correctly simulating cell chemistry and packaging. Having understood the cells enables us to avoid ignition of the flammable vented gas in the case of a local thermal runaway by implementing measures that guide the gas such way that its temperature drops quickly and that it can leave the pack without delay. Also, we want to capture ejected particles, as they potentially can, ignited the venting gas. Another ignition source are electrical arcs occurring because of short circuits. The high voltage path, therefore, must be separated from the path venting gas takes in case of a cell thermal runaway. The proper use of insulation material could slow down and limit cell-to-cell propagation. Implementing dedicated heat sinks is also a mean to help stopping a thermal runaway. As you can see, our solution for a no-propagation design of batteries is strongly supported by simulation. But AVL also offers conducting physical tests required to characterize battery cells. These tests can be conducted in our AVL Battery Test Center. Before coming to the end, I'd like to direct your attention to our recent efforts about modeling, arcing, and particle ejection. Both features are extremely important to discover thermal runaway that are not based on heat conduction from cell to cell, but more based on the venting gas particle exertion from the battery. This kind of thermal runaway follows different time frames and different spatial locations, meaning a battery cell could ignite at one end of the battery pack, but the thermal propagation starts at its other end. Looking at battery thermal runaway therefore requires modeling also particle ejection and arcing, as these phenomenon could lead to problems in regions you initially may not have paid attention to. Already briefly indicated when talking about one of the previous slides, I like to highlight now that our battery solution goes beyond our 3D CFD software FIRE M. To balance speed and performance and to meet specific requirements during all stages and for all tasks in the battery development process, we provide consistent modeling capabilities in both our 1D system simulation software Cruise M and our 3D component simulation software FIRE M. With FIRE M, we help you reaching your targets in battery development and optimization. Our solution comprehensively models thermochemistry and flow effects in batteries and focuses on developing safe batteries. Our high-fidelity models allow going into details if needed. Balancing speed and performance during all stages in the battery development is achieved by providing modeling capabilities applicable in 1D system and 3D component simulations. And not to forget to mention, we are always with you, not only virtually. A worldwide network of real AVL simulation experts is available to support you in doing your day-to-day business effectively, efficiently, and timely. With this, I'd like to thank you for your time and your attention. I'd be happy to have in-depth discussions you on how to use our simulation solutions to support your battery development. I hope to see you soon again.